why would we ever want to use Metal? And what is it useful for? Well, Metal is first of all is Apple's kind of proprietary GPU API. Before it was introduced in 2014, I believe. Before that, iPhones were running OpenGL ES, and that's just an OpenGL version for mobile devices, basically. But Apple decided to come up with its own API. There are benefits obviously to this because they can have a tighter integration between their hardware that they also produce themselves these days and the software.
Recording is on.
So yeah, Metal came up with its own API in 2014, and they ported most of their frameworks to this API. So you can, if you ever use, for example, SpriteKit for 2D games, or Synchy for 3D stuff, or even Unity these days supports Metal. And you kind of want to support Metal to run as fast as it can on Apple hardware. But why do we want to use a GPU? It's okay it's fine that we have a API to program the GPU, but why would we want to use the GPU in the first place? Well, GPU is a piece of hardware that's optimized for parallel computation, and what that means is that instead of just having 16 cores on your CPU, the GPU will have thousands of cores, and those thousands of cores can run in parallel and have just basically having parallel threads of execution helps out with when you want to process data, but the data doesn't depend on each other. So if there is no implicit data dependency between just between pieces of data that you want to process, it makes sense to compute everything in parallel, so you don't waste the CPU cycles to compute something that can be done in parallel, basically. You can see here I have a diagram. Where's mine? I can have a diagram in the upper right corner, and that's kind of a high level overview of a AMD GPU. So basically, you can see that it consists of multiple layers, but those compute unit layers, those blue ones, in this particular GPU, one compute unit is 64 cores, and there's 36 of them. So if you do the simple math, that's close to 2,300 cores of just processing power. Obviously, they're not as powerful, nor are they as sophisticated as CPU cores, but they're cores nonetheless. So you can have 2,300 threads executing your code at the same time. And now compare that to your 8-core CPU. It's just it's so much faster, but you have to make sure that you use it in the right way. Another reason to learn Metal is not just for graphics, but for general purpose GPU computing, and that's a new thing. It hasn't been around as it hasn't been around just like graphics, but it's becoming a new thing because you want to, for example, train your models on a GPU, because machine learning models, they use a lot of computation, and GPUs are optimized to do that kind of computation. These days, people also come up with special cores for just to train machine learning models, but they kind of resemble GPUs, but have some minor differences. But the fact still stands that more cores, more data you can process in parallel, basically. And that brings me to my first demo. I just want to show you guys. Just want to show you guys how ridiculously fast GPUs can be. So here I have a little program. Basically, I have this array one and array two, and I populate them with 4,000 values, plus or minus. And what I want to do is I basically want to sum up the array. I want to sum the first entry of the first array with the second entry of the second with the first entry of the second array, and put it in the third array. So what I would do on this my regular program is I would have this for loop, right? I would iterate from 0 to the size of the array, and I would take the first value from first array, take the same value from second array, sum them up, and put them in this result array, and this will kind of do everything in once. But there is no reason to do this operation once because, as you can notice, I don't, and my data is independent. So it doesn't. This array doesn't depend on this array in any other way. So it doesn't hurt if I can do this line of code, literally this line of code, um, uh, in all at once on different values of I, and that's basically what GPUs let you do. You can see here, a Metal uses like a subset of C++ um, for just to write the code for it. So you can see here, I literally have the same line um, as here, but you don't see any for loops here, which means that Metal, it takes this uh, function that I wrote here and distributes them to all its 2,000 cores or whatever my computer has, and it all runs at the same time in parallel, which is crazy. And instead of you still need to index the array, and that's where Metal kind of gives you um, this position in the array, and then you can use it to index. But as you can see, no for loops whatsoever. Uh, and if I run this code, you'll see I have some output here already. So you see here that so it took this many seconds to execute on a CPU, and it took this many seconds to execute on a GPU. One thing you can notice is that actually the GPU took longer, and you could call me out for that, saying, Maxim, you lying to us. The GPU is not as fast as on the CPU, but all this code basically that I wrote for Metal, it has a high overhead. So, for example, this you need to compile this function, right? When I say this, like I make this function, I'm basically compiling it, and all these structures that we'll talk later um, about kind of take it's a big overhead. But because I'm just computing 4,000 values, the CPU is perfectly fine with computing 4,000 values. But let's say instead of 4,000 values, I compute 4 million values. See how that changes. Now look at that. The CPU took 1.5 seconds, and then GPU took literally the same amount of time. Like if you compare it, like we had 6 hundredths of a second before for 4,000 values. Literally took the same time to compute 4 million values. While the CPU, I don't know how like magnitudes of longer. I'm not sure how much more we can go, but you get the idea, right? The GPU is ridiculously fast, and that's kind of the intention. That's why you want to learn how to use this API and any other API that deals with the GPU. So I don't really want to wait, but I think I tested it for this value, and it was sort of like the same amount of time for the GPU, which is insane. All right. Um, so that's kind of the motivation to why you want to use the GPU. Um, so when it comes to graphics, um, there are a few stages. The graphics, and it's called a graphics pipeline, and Metal has one. And it all starts with this data that you pass into your GPU. It does some stuff on it, and then it comes up with a picture on your screen, right? And the way it does it in Metal is through these stages. These are the primary stages. The GPU can actually have more stages to that. This is definitely not it, but this is just a high overview of how it works. You can also see here that some of the stages are called green. The stages that are called green, we have full control over. And the stages, for example, rasterization, we let the GPU handle rasterization for us, and we can't change this stage as well as blending. But going one by one, we have just simple, putting or sending the GPU the vertex values to the GPU. We have a Vertex Shader, and shader is just a fancy word for a function. Like 30 years ago, they all the shaders were just used to color the pixels on the screen, and like color means shading the values on the pixel. And kind of well, that's not what GPUs are used for primarily these days, but the name kind of stuck around, so that's why we call functions that run on the GPU shaders. So we have a vertex shader. The vertex shader just processes all the vertices in parallel. As I said, you can do uh, uh, you can basically multiply them by whatever matrix you have uh, to rotate the scene around, uh, to make things bigger, make things smaller, make sure that you got the perspective right and stuff like that. Tessellation is a more like an advanced topic. I see you can see here I have a little picture. It's basically like if you want to model terrain, instead of just sending all these vertices, all this data to the GPU, you can actually make the GPU come up with the vertices for you. So instead of sending all this data, you let the GPU generate the data itself. Data, oh, by the way, data comes with an a buffer. It's just memory, and you tell the GPU how the memory is used. So usually it's organized into vertices, and the vertices have a color, they have position, maybe some pattern, just the compiler would add its own pattern to it. Um, but basically it's just a blob of ones and zeros, and then you tell the GPU how to interpret that blob of ones and zeros. The next step is rasterization, and that's basically when you modified all your vertices, you actually you at the end of the day, you want to color pixels on the screen, and a rasterizer it basically figures out how to what pixels to cover for each object in your scene. So, for example, if you have a triangle here, you want to figure out what pixels are inside the triangle so you can color them, right? And once you figure out what pixels you need to color, that's when fragment shader comes in, and fragment shader runs on every fragment on every single pixel. Um, on your screen, and then you can manually adjust the color for every pixel on your screen based on what the rasterizer came up with. And then blending is also more of an advanced topic. We're not gonna talk about it that much, but the basic things that you want to do when you doing a graphics program is to come up with your vertex shader and your fragment shader, and that's what we're gonna do in code today. This is how the API looks like. The Metal API, you have something called a command queue, and that's just a regular queue that we used to. You push commands to it, and the commands are guaranteed to execute in the order that they got into the queue. So if you push this command first, this command is going to get executed, and then this command is going to get executed, and this. The command itself is consists of a command buffer, and the command buffer has all the information that it needs to execute your command. Um, it's kind of The API is really cumbersome in terms of how many objects you have to create. But in order to encode your command into the command buffer, you use something called an encoder. And here you can see there's a render command encoder. The demo that I showed you a few minutes earlier used the compute command encoder. That's because all I wanted to do was to compute stuff. And the render command encoder, I would go through all these stages before it comes up, before the command is marked as executed. Um, what do you want to put in your command buffer? Well, you want to put your actual data, right? Like the Vertex data. So this is where you encode your buffers. Sometimes you want to put textures into your command buffer in textures such as imagine like you have a sphere, right? And then uh, imagine you want to have a 3D 3D basically representation of the Earth or something or a ball. Uh, that's where textures come in. So you can map, Atlas basically, the map of the Earth onto your sphere, and the map of the Earth would be the texture. There is a sampler state, which is how you sample your textures, which is also a pretty interesting topic. Depth stuff. How do you make sure that you know what object comes first? Because like it's a 3D scene, right? So some objects come first, and some come are closer to camera. Some objects are further away from camera. And how you determine that is a depth. And then there's the render pipeline stain, which is kind of main uh, the main thing that goes into command buffer, and that tells you what vertex shader, what shaders to use, and yeah, and then how the pixels are represented on the screen. So that's it. Let's let's just write some metal code. I think time. Let's see. So what you want to do is you want to make a new project. I'll call it metal example or like a triangle. At the end of the day, today we just want to put the triangle on the screen and color it. So, but once you have the triangle on the screen, once you set up everything you need to set up, moving further away from the triangle is really easy. So and make sure you have your storyboard selected and language Swift. And there you go. Need to pull up in a sec. So okay, I already have all the code uh, here. So and since my sidecar refuses to work, I'm gonna have to reference it from time to time. Um, all right. So the first thing you want to do is you want to open up view controller and import MetalKit. Uh, MetalKit is just a wrapper on Metal, and it lets you use your Metal classes as your kit classes, basically. So there's something called Metal View, which is a MTK view. It's a subclass of regular, so for Cocoa, it's an S view. For UIKit, is a UI view. It's just a subclass of this. Uh, and what you want to do is you want to add it to your view, basically. And every time it updates, you want to see. Okay, so this works. You also want to set the delegate, and we'll create a new class. We'll call it a renderer. It's an subject, and you want the renderer to implement the MTK view delegate, and that's what allows us to set it as a delegate. There you so basically, let's see. The second thing you want to do is create a device, and device is just a software representation of your GPU. So that's what Metal uses to communicate with its GPU, and it's just an abstract representation. You can see here it's the type MTL device. You can think of it, it's just our GPU basically, just in code. Um, you also want to set the device on your Metal view to this device. It also helps to helps to set a clear color. A clear color is basically what the color is, because once you write once you write the write happens every frame, right? That's how just rendering works. Every frame, let's say 1/60th or 1/24th of a second. Just iPhone, actually, iPad Pros, and iPhone 13, and now new MacBooks. They all have promotion, um, which with adaptive refresh rate. So and that timing for each frame can actually be different this time, but so just the rendering speed can also be different. But what never changes is, and once you render something on the screen, you want to clear the screen because and render something else in another frame so that all so that you don't accumulate all that rendering. And that's what clear color does. It resets the screen to this color and then lets you render again into that screen. Um, MCK view delegate, there are two methods that you need to implement. Um, let me talk about this first. This is we're not going to use today, but this basically says every time the bounds of the view change, do something. Um, and this is the primary method that we're going to be using today. This draw method is supposed to be called on every frame. So every 1/60th, my monitor is 60 hertz 60 hertz. So 1/60th of a second. This is going to be called, and we're going to draw into here basically 60 times a second. And this is where we do this in this method. So let's see. Um, we'll see basically. So the first thing we want to do is create all the stuff that we need for our pipeline. It consists of the command queue. So you use let's see. Actually, so you need a command queue. This is of type MTL command queue. You also need pipeline state, um, and it's going to be specifically a render pipeline state. You also need That's it for now. So let's try a little select constructor. And we'll say Q. You would just use the device to make this command Q. Make command Q. Bang. I mean, for obviously for a production app, you won't use this, but for now, this is fine. There is also you want to call super.init, obviously, and I'm gonna make a separate function to make the render pipeline state. Actually, let me see. It's easier if I. So basically, this function makes this pipeline state that we talked about. So what it does, I first create the library, and the library is it's a fancy word. By the way, it's also a good time to create a new metal file. I'll call it shaders. So this is where we write all the shaders for our program. So basically, what this make default library does is it goes into your bundle and searches for all the metal files it can find, and then it compiles them into a library, and that let us kind of extract the shaders that we need for our program. So as with any other metal objects, you create a descriptor just for the pipeline state. You set your vertex function by calling this make function method on the library, and you pass in the name of the function. So later on, we're gonna have something like a vertex, um, uh, like something like vertex main, and this is going to be the name of the function. So that's why we put here vertex main, and then for the fragment function, we're going to have a fragment shader. It's going to be its name. Um, just don't worry about this. This is how we will represent pixels. And then you call or make render pipeline state with a descriptor on this device, and and then that returns you a pipeline state. Let's see what other objects that we need. Okay. So basically, you create these three at the end of your program, and you cache them basically. So you don't need to recreate all of them again and again, and that's why Metal is so performant. This setup allows you to create this library, create your queue and pipeline state before your program gets to execute at the start of your program, as opposed to OpenGL or that has to do this process every single frame. So imagine doing this 60 times a second. And as I said, this is a big overhead. That's why it took so long to process just 4,000 numbers in the first demo, because this is a big overhead. This takes a long time to set up, just in terms of CPU cycles. So doing it every time here is highly inefficient, and that's what basically OpenGL does and Metal does, and that's why it's one of the reasons why it's way more performant than OpenGL. So here, you first want to extract your drawable, which is just a property on this view that's passed in, and drawable is just a low level buffer that you write to. So that the view can use to update itself. Then there's also a path descriptor. And that kind of has all the information about just the setup, how the pixels are laid out and stuff like that for this view. You also need, as I mentioned, a command buffer. So you call your queue, right? And then you say make command buffer. And finally, you need a command encoder, render encoder, and that's make render. And the descriptor is just this path descriptor that we said. And else we're just going to skip this frame. This basically means if nothing of this exists, just drop this frame. Don't render. Uh, so these four things that we need. So, and we're going to be using render encoder to encode commands into command buffer. And the command buffer is going to be sent to the queue. The queue is going to send it to the GPU. The GPU is going to execute the command. And then we're going to be, and then write all the data to the drawable. And the drawable is going to help out the view to render itself, basically. So let's see. Yeah, so the first thing you want to do is you want to set your render pipeline state, and that's what we create here. And you can see why we need to encode this, because this command buffer needs to know what functions to execute, and that's where the, we store the functions in this pipeline state. You also want to do other encoding, like perform something called a draw call. And the draw call is you basically say draw this for me. At the end, you want to say I'm done with this command, and then you want to commit it to commit the buffer to the GPU, and then you want to wait until it's completed, or you can just set a closure, basically a callback to do to notify you when this command is complete on the GPU. So this was just set up, not too exciting, I guess, but this part of the rendering loop is the most fun, at least that's what I think in my opinion. Um, let's see. I'm also not sure because we should be getting. Uh, so also, I think it's time we can. Well, do you want to do this? No, we'll wait. So basically, as I said, now you want to come up with some data for the GPU to process, right? Because that's what we're trying to do. And the data is going to be just the vertices of a triangle. We want to render a triangle on the screen today, at least. And the triangle consists of 3 points, right? You have 3 points to draw a triangle. So we need a vertex for that. And here's the easiest thing to do it, because you want to use the same data structures on your GPU and on your CPU, so that you don't have any alignment issues or stuff like that. It's also you don't have to write code multiple times. So what people do is we create a new header file. We'll say it's shader shader definitions. Um, and we're going to declare a new struct. And for now, I'll also import SIMD. Where's my type completion Xcode? Come on. So SIMD stands for single instruction multiple data or something like that. Basically, just lets us have stuff like vector flow 3 addition. Basically, just this vector flow 3 is a vector with 3 values in it, x, y, and z. And we call this vertex in. See if this compiles. Nice. So what this header file lets us do is, if we go to our project build settings and search for bridging header, um, so if we specify this bridging header, this is going to kind of bridge between C++ or Objective-C for that matter and Swift. So everything we declared here is going to have its Swift version um, in, uh, in our actual code, and then we can use the same file for um, in this C++ kind of metal file. So that kind of simplifies things a little. So what we want to do is we want to say usually objects are consist of mesh, and mesh is just a collection of vertices. Um, so we want to say for the see how I already have a vertex in, even though I didn't create a struct in Swift, um, and that's what kind of the bridging header does. I want to specify the position. Um, yeah, just gonna copy it real quick. So basically, we'll create an array of these vertices and specify the position. Let me add the color real quick. We're going to use color later, but don't worry about it for now. So we specify the position, and the position it's usually a normalized canonical coordinate. So that what that means is you have your x and y values, your x, y, and z values, so between -1 and 1. And so you can see here that x value is 0, y value is 1, and then z value is 0. Z is going to be 0 for now. We don't deal with 3D stuff yet. But you can see here x is 0, y is 1. That means it's going to be right in the center. So this top vertex for the triangle. This -1, -1, negative x and negative y. So that's bottom left corner. And 1, -1, it's on the opposite side. So you can kind of see how diversities make up a triangle. So now you need to send this to the GPU, right? For that you need to create a metal buffer. So I'm just gonna say uh, there is a buffer. I can call it mesh buffer because this only exists on its data defined on the CPU. Um, and mesh you kind of need to use mesh buffer to send the data to the GPU. Um, so you need to initialize it first. Oh, my bad. Of course, it was in the renderer. So what you do is you say mesh buffer and use the device to create this mesh buffer, uh, and you specify the bytes. Uh, and this is just a pointer into your array, and the length is going to be memory layout of the vertex, right? Um, so what I do is Swift implicitly the compiler converts this array into a pointer for me. Um, so I specify this pointer to this array. I specify the length of this array, which is consists of vertex my vertex structs times the count, right? Um, and then on a storage more shared means that the CPU and GPU can share the memory. Why is it yelling me? And now you need to set this buffer on the render encoder. So specify mesh buffer offset 0 and index is 0. So index 0 meaning it's the first. You'll see why it matters in a little bit. So now we want to create our vertex shader. I'm just gonna copy and paste it real here. So basically, what you have here is a vertex shader as specified by this vertex attribute of the function here, uh, and and then the vertex you specify your buffer within these kind of brackets, which is not a standard C++ syntax. but that's why it's a subset of of C++. So it's yelling at me because I didn't import our shader definitions. Yeah, so you get this array of vertices, and you get the ID for each vertex. Um, so what you can do is you can say vertex in is just index this array, and then every vertex function, every vertex shader needs to return a vector of size 4, and it's of size 4 because uh, it's kind of a fourth dimension, but the GPU uses this fourth dimension for perspective and stuff like this. Um, so we basically can say float 4, and then we can input the position and just specify 1 for the fourth coordinate. And what it actually does is it takes this coordinate here and divides it by this vector, by this position vector, and that's how you can achieve perspective in your scene. Um, and then for now, we can say we can write our fragment shader, which is a shader that runs pixel by pixel. We'll call it name. Um, and here we need to return. I mean, logically, if it runs on every pixel, you need to return the color for that pixel, and the color specified also as the vector with four entries in it: red, green, blue, and alpha. So for now, I'm just going to return a red. Uh, yeah, I'm going to return red, and one alpha. Are you yelling at me? Oh, still nothing. Let me see. Oh, that'll do it. Why do you refuse to work on? Anyway, I have no idea. So I have a version of this code that's actually working. So we can continue with this, and then I'll show you kind of the final product. So here, let's kind of sum up what we do here. We send these vertices to the 12 vertex shader. The vertex shader for now just takes these vertices and just adds one to it to create this float 4 vector, and then it goes to the rasterizer. The rasterizer rasterizes the triangle for us, right? And then it calls this method. It calls this fragment shader for every pixel that it thinks it's inside the triangle. And for now, we just want to return uh, the color for the pixel, which is a static red color.
Maxim, I think you're not presenting the drawable at the end of your draw method.
You're right. You're right. Thanks. Yeah, thanks for that. Good catch. So you can see here we just return a straight red color. And I'm also not making the actual draw call, right? So to make a draw call, you want to use these like the render encoder has all of them. We're gonna so for now we're just gonna go simply with drawing the triangles. Um, and the vertices start at index 0, and they all go all the way to mesh account. Let's see. Right, and then, see, I think make it a little like gray background. Yeah, so you can see here that we have our triangle finally. Um, but you can kind of see how you can see this is pixelated a little. Um, that just means we haven't specified any anti-aliasing options. Because I mean, at the end of the day, you want to draw a line from this vertex to this vertex, but it's a grid of pixels, right? So you kind of just logically assume that this should happen. The reason that you can really see it in modern graphics is because they enter this is called aliasing, and you do something to do is you do anti-aliasing, right? So and that kind of gets rid of this problem by setting some of the pixels nearby this line to red color, but not as intense. But we're not going to do that today. Let's see, what else do I want to do? So we have 9 minutes left. I really want to get to um, I want to get to what's it called? Interpolation. Yeah. So let's do that real quick. Um, so basically, another useful thing that GPU does for you is it interpolates the values that come out of the vertex shader, and it's used for different reasons. Sometimes sometimes you have a surface, curved surface, something, and you only have normals at some points. But in order to calculate shading, in order to calculate lighting effectively, you need a normal basically at every fragment. And but since you can't really specify more normals than you have vertices, you need to interpolate them, and it interpolates everything that comes out of this vertex shader. So what I can do is I can interpolate the color. So I can say instead of returning a float, I'm gonna return the vertex out, and you can see vertex out. It has this position thing, and that tells the GPU that this is the position. Because you need to return the position anyway from the vertex shader. You just return the struct that has a position in it, and then the GPU would interpolate all these other values that you have here. So I'll say uh, position is going to be the same thing. And color, color is going to be, I'm just going to pass in color. And so basically, once you return this, the GPU rasterizes it for you and passes it into the fragment shader. And the fragment shader receives this value. You have to say it's staged in, so that it knows where to get this value from. And then basically here you can just let's do this. I'm not sure why I have floor 3, but we'll see. And then alpha will be static 1. Yeah, so you can see here that so what I have in code is I have these 3 vertices. These vertices, the top one has color red, then this one has color blue, green, and this color has this vertex has color blue. And what the GPU would do for me, it would rasterize, basically interpolate. The colors between green and red for this region, and but it wouldn't touch blue color because it's on this line. And then um, and then it would do the same thing for this, and then colors in between. So you can see how the color changes from red to yellowish to greenish. And you have the same thing here for the purple and magenta. So that's pretty cool. That's a really useful thing that that the GPU does for you. And then real quick, I also want to make sure we get to animating stuff, because that's also what we use the GPUs for. So So how you animate stuff is you basically change the positions of the vertices and your vertex shader, and yeah, and on every frame, and that's how, and then the GPU renders the same triangle but with different vertices. So here I want to just spin the vertices around. For but in order to spin them around, I need to change the position of these vertices here. And the way I do it is I basically use a matrix. So computer graphics is like 9% linear algebra. Just right. So you basically use a rotation matrix to rotate these points around. And the rotation matrix, people put them. You can put them anywhere, but people put them in uniforms, and uniforms are the values that are not necessarily like vertices, but you want to use them in your shader. You can have multiple values here, but for now I'm just going to have the smaller matrix, which is going to be our rotation matrix. And I have this function. Yeah, so I have this function here that creates a rotation matrix for me. So this is a 3D rotation over the y-axis. No, z-axis. Sorry, yeah, this is a rotation around z-axis. Um, so now we have this now we have this matrix. We need to send it to the GPU, but um, you don't want just statically rotate. You want to you want to actually animate it. And the today I wanna we're gonna be using time based animation. Um, yeah, and so time based animation is when you interpolate the values for your animation parameters based on how much time has passed since your last frame. It's useful because the time that's passed and that you can dynamically adjust it. It comes in handy, especially when you have these promotion displays that can adjust the timing between each frame. So your animation depends on the timing between each frame and not something as some absolute value. So I have this setup where you have the time from the last render. You have current time too, and I want to interpolate this rotation angle. So what I do is on every frame, I calculate this delta time. And delta time is how much time has passed since my last frame, and then I pass into my update function. And the update function, basically it takes this rotation angle and it interpolates this rotation angle between 2 pi and 0. So this is just like a generic formula for interpolating a value. So you want to go from the end from the end. Uh, yeah, this is the end value. This is the start value, and you want to go delta time fraction of the basically that's the fraction of how much you want to go from here. This is something called time-based animation. You can look it up. Yeah. Also, last thing, I also need uh, I need a buffer to send it to the GPU. Uh, yeah. Okay, so I do the same thing as with my vertices. I create the buffer, but now I calculate values real time. So I just specify the length of my buffer, and here I create this uniform struct that I have in my shared definitions, and I copy it into my buffer, basically. Yeah, so the contents returns the pointer to the buffer, and then you specify um, the size and the how much memory you want to copy to that pointer, and then that does it for you. Um, so last thing is you want to send this buffer to the GPU. So you say set vertex buffer. Um, what do I call it? Fragment. Uh, no, vertex uniform buffer. Offset 0 by index is 1 now. So since it's in my index of 1, um, I can say uh, what was it? Vertex, yeah, vertex uniform. So reference to, um, and then I say it's in my buffer number 1, right? So I now I can use this uniform here. So what I do is I pull out this matrix that I have from the uniforms model matrix, and I multiply it by it's 3 by 3. Never mind. Yeah, so I take this model matrix and I multiply it by the position, and that's how I rotate them. But notice how I do this multiplication in my shader and not on the CPU. I could have easily done it on the CPU, but that's the whole point of using the GPU, so you can parallelize this computation. Um, that works. What the hell is this? Oh, yeah. Yeah, you want to make sure you set all the buffers before you actually issue a draw call. So there you go. Now you have rendered a triangle. You have interpolated the color values, and you also using time-based animation to animate this whole stuff.